Okay, so this is section B of the 2018 electronics end of year exam. It's the first booklet, so this is criterion 4. So we're not going to look at question 8, this is, or 8A, because this is a capacitor question which we haven't covered yet. Part B, we've got a circuit, in a circuit 82 ohms, 18 and an 18 ohm resistor are combined to replace a 100 ohm resistor. How are they arranged? Well, in order to give 100 ohms, you just add them together, which would result from a series arrangement. Two 100 ohm 1% resistors have been replaced in parallel to each other with the aim to replace a 47 ohm 5% resistor in a circuit. Describe one advantage and one disadvantage. So the advantage I can think of for this is where we haven't really been told what the power rating is, but if assuming that they're all the same, then the 100, so the 2 times 100 ohm could dissipate more power. All things being equal. So if these were like quarter watt resistors or something like that, then we would be able to get half a watt of power dissipated through the two 100 ohm resistors. The other disadvantage of this is that it may not actually be the 47 ohms that is required. So two 100 ohm with 1% would be 50 ohms with 1%. So may not be the same value. Actually, it will not be. Oh. So that might be a disadvantage. This would be the advantage. Okay, so here's a circuit. Now this question I thought was quite challenging, particularly for the expectations of students to know what circuits are what, and in this case it wouldn't be expected that a student knows from or recognises this is an SR latch configuration of the circuit. So but we should be able to recognise what these components, X and Y, they're both 2 input NOR gates. However, in this circuit, it's an SR latch circuit. However, I didn't think that this is a reasonable expectation that students understand or remember that is what it is. If the students were told what it is, they should be able to understand its behaviour though. Okay, so we've got a switch being added to the circuit, and this will control the outputs of X and Y. And so we're going to show how the switch can be connected to achieve control. We need to add resistors and voltage rail to any additional wires as needed. So an SR latch, if we set one input high, it will set one of these outputs high, and if we change it so that the other input is high only, then it'll change the other output to be high, so it'll toggle it. And when we set both inputs back to low again, the configuration will hold its state. Now these crossover feedback wires that you can see here, they are that feedback there is what causes it to hold its state. So once we set one of the sides and then set it back to 0, then that will hold its state. even if the inputs go back to low again. Okay, so if you can see here, they've lined up the reset on the top side of the switch here, and it's fairly arbitrary which of these outputs we call the Q and not Q. But based on this reset and the fact that that's a NOR gate, if this is logic 1, then that'll go logic 0, and so we would probably assume that this would be the Q output of our SR latch, and this would be the not Q, the complementary output. So if we set the is input here to logic 1, then we need to connect that to the positive supply. Now the problem we might have here, and this I would expect that you should understand and recognize, is that when the switch is in this current position, you see that the set input pin is not connected to anything, it's floating. So we really need to use a resistor connected to something. So in this case I'm going to connect it to ground to make this logic low when the switch is open, rather than being a floating switch. If we were to change the switch position, so now it's connected to set, the reset would have the same problem. So we should do the same thing on that side as well. So these two pull down resistors, the value isn't super important, just need some kind of resistance so that we don't have these floating inputs. Now this is another circuit that actually behaves identically to the SR latch above. So this is what we call a NOR latch, and this is a NAND latch. So these are going to be 2 input NAND gates. Okay. So this part E here is probably one of the more challenging parts of this, because unless you've done it before, it can be difficult to sort of know where to start and what to do. You're certainly not going to be able to figure out just by sort of looking at all. So I'll give you some pointers on how to work through a problem like this where we've got definite states. So what I'm going to do is I'm going to start with a B, and what I'm looking for here, if we look at the NAND flip-flop, if we've got 2 inputs, which I'm going to call X and Y, and the output of my NAND gate, and these are the 4 possible input conditions. The NAND gate, it's when both inputs are 1, the output goes to a 0. So when both inputs are 1, the output goes to a 0, otherwise all of the outputs are logic 1. Okay, so you need to remember the truth tables of the different 2 input logic gates. So this is the truth table for the 2 input NAND gate. And so what I'm going to do here is, because we've only got one very particular case where the output can be 0, I'm going to look at where B is 0, because that's the output of my first logic gate. So if B is equal to 0, what this implies is that A is equal to 1, and also C is equal to 1. But you can see that A is connected to the output of this second logic gate here. So if C is equal to 1, then we already know that B is 0, but we don't really care what D is. So I'm going to write that as an X, meaning don't care. So D can be anything. As long as C is 1, this B will be a 0. Okay. Likewise, what we can do is, let's consider when A is 0 now. Okay, so we're going to do the same thing, but now looking at the output of this second logic gate. So if A is equal to 0, that implies that B has to be equal to 1 and D has to be equal to 1. Now in order for B to equal 1, that's this one here. Alright, this is the output of this NAND gate. Well, A, we already know that. A is 0. But C could be anything. C could be either 0 or 1. So C, we don't care about. Okay. If the logic level at point A is required to be opposite in value to the logic level at point B, okay, so in order for, so let's just make sure we've answered the question. Explain what logic levels we need to be each C and D. So here we've got, so if B is 1, we don't care what C is, but D has to be 1, okay. If B is 0, we don't care what D is, but C has to be 1 and A has to be 1. Okay, so if A is 1, then C has to be 1. Okay, so we can summarize this in a little statement. So if A equals 1, then C has to equal 1. If A equals 0, then D has to equal 1. Okay, it's a D there. Okay, this is an op-amp question, so I'm not going to do that one. Another op-amp question, so I'm not going to do that one. Okay. So this is a microcontroller. So it says pickaxe there, 08M2, that's the pickaxe microcontroller. And it's expected that you recognise that the pickaxe needs 5 volts with about half a volt of tolerance on that power supply. Okay, so when powered on, which leg of the microcontroller will clock the integrated circuit? So the leg is the number, the actual pin number, or the connection number on the actual microcontroller chip itself. So these are represented by these numbers around the outside. So if you think about a microcontroller integrated circuit, we've got these legs that are the electrical connections to the microcontroller, and for the 08M2 being an 8-pin chip, they would go in this sequence like this. And so these are the leg numbers, and so you can see here that leg 7 is designated as pin 0, so this is the pin number. Okay. So we're asked which leg it's connected to, and it's connected. The clock is connected to pins to leg 7. So okay. So in the program, if it said high pin 7, there's 2 reasons why this wouldn't work. One is there is, so output 7 or pin 7 doesn't exist. That's because these are referring to the pins. Okay, and so we've got 0 through to 5. So 7 on an 8-pin pickaxe like this doesn't actually exist. The other thing is that, and I wouldn't expect this to be necessarily known, but however it's also a correct answer to this, is that pin designates as an input. So I'm just going to put inverted commas around that. So pin designates, so this word pin here would turn this into an input. So even if there was a pin 7, I wouldn't be able to set it high because calling it pin makes it an input. So stating two advantages of circuits that use microcontrollers as compared with dedicated components. So for example, logic gate ICs. So the main and probably the most obvious one is size and complexity and expense. So if I were to make like a counting circuit or something like that, I'm going to need multiple flip-flops or counting circuits, and I might even need logic gates and things like that. And all of that would require multiple chips, design, um, a larger PCB, which is going to get expensive. And basically, whenever you add size and complexity, you're going to add expense to both the size, to the manufacturing cost of the project, as well as the design of it. So the second benefit, though, and this is also a very powerful benefit of using programmable circuits, is that you can easily change, within reason, the function or the functionality. So all you need to do to change the functionality is reprogram it. So for example, if you wanted to change the time on a delay, or the how the modulus of its counter or something like that, that might just be a matter of changing the program that you've uploaded to the pickaxe. Whereas if this was actual built-in hardware, it might require a complete redesign, if not even starting from scratch again. So it's much easier to do that. So it's certainly from a design perspective, but also from a testing and a updating. So it's relatively easy to change the software in a thing, even once it's been built. If you have the pickaxe being socketed, so you can just pull it out and reprogram it if you don't have a programming port built in. Okay, so part E, leg 8 is labelled VSS. So VSS, that one there, that is the source voltage. Okay, so VSS is the source, which means the zero or negative power supply connection. So VSS and VDD, source and drain, are quite often used for CMOS type circuits, and it's a labelling, it's a sort of a naming convention for the power supply connections. And source and drain sort of implies that this is the source of electrons. So electrons are going to be flowing into the source pin and out of the drain. So the electrons are being drained from the VDD connection. Okay, question 13. So this is a power supply circuit. So we've got the circuit diagram there. Part A is asking what the components bounded in the dashed box, it's on the left there, represent which electronic part. Well, that's a transformer. And what we would see here is we've got this third pin on the middle here, and that's connected to ground. So we call this a center tap transformer. And what we're going to have on this side is an AC waveform that's 6 volts on there. And on the other side we can have another AC waveform, but it's going to be the inverted waveform of this. So it'll be basically the same sort of waveform, just upside down. And now we're feeding this through a diode. So this diode here is only going to conduct on the positive part. So in that shaded area region there is what we're going to see here. So this little bit here would just be like that. This little bit here does the same sort of thing, but you notice that this is now at a different time, so it's going to be for this region, and so we get that part of the waveform, and these are going to combine together here to give us a waveform a bit like that. Now with the capacitor here, this C1, what that is going to do is it's going to charge up across when the peak of the waveform is, and then it will discharge through our circuit, our regulator circuit, and as it discharges the voltage will decrease a little bit. And so what we'll see is, well, suppose let's look at the timing here. This is a 50 Hertz signal. That means that it repeats every 0.02 seconds. 1 divided by 50 is 0.02. But that would be for this sinusoid here. And so each of these bumps, or half a waveform, happens in 0.01 seconds. So it's going to go up like that, and then back down again, and then up like that, and back down again. Okay, so that's what it would look like if we didn't have the smoothing capacitor there. But with the smoothing capacitor, what we'll see is that it charges up, and then it'll discharge a little bit. And charges up, and then discharges a little bit. And so we're going to have, several charging and then discharging like that. Okay. So this is going to be the smoothed rectified waveform. So C1, its purpose is to do the smoothing. So it smooths the DC voltage from the rectifier. Okay, to prevent damage to the 7805, a third diode must be included if the power supply is used to charge a battery, and it is then switched off when it's while still connected to the battery. So the thing that would get damaged here would be this regulator in this case, and the reason why it would be damaged is because the output voltage would be higher than the input voltage. Now there's two ways we can protect it, and I'm going to label them D3 and D4. So label D3 and D4 as shown. So the easy way, and this is probably one way that makes the most sense, would be to put a diode in that direction there, so current cannot flow backwards. The other way that we could do it, let's call that D3. The other way we could do it is make it so that if we did have a large voltage across here, or a larger voltage here than here, then the voltage will be conducted in a pathway that won't damage the regulator chip. So we'll call that D4. So either of those would be a solution to the problem. Okay, question 14. So we've got a D-type flip-flop, and we've got a timing diagram or a truth table for it here. And there is a mistake with this one. Both of those should be not a positive going edge. Okay, so we've got our positive going edge here and not a positive going edge here. Okay, so on the symbol or diagram above, we're going to show how the flip-flop can be wired to function as a T-type flip-flop. So what the T-type flip-flop does is it toggles its output, so it changes its output. If the output is 0, it changes it to a 1. If the output is a 1, it changes it to a 0 on the positive going edge of our clock signal. Looking at the truth table here, you can see that if D is 1, then the next Q is going to be a 1. If D is a 0, then the next Q is going to be a 0. So that's what I'm looking at there. D is 1, Q goes to 1, D is 0, Q goes to 0 on this clock edge. If it's not that, there's no change. That's what these ones here indicate. So what we want is that if the output is 0, we want it to change to a 1. So what we need is that when the output is 0, the D is a 1. And the way that that happens is by looking at here. You can see that when the output, if the output is 0, not Q, is a 1, and so we connect that onto the D. Okay. Similarly, you can see if the output is a 1, so if Q is a 1, then not Q is a 0, which is what we want to change our next output to 0. So connecting this like this will change it to a T-type flip-flop. Okay, use the truth table above to describe the D-type flip-flops when the clock goes low. So that would be in one of these conditions here, where it's not a positive going edge. So the outputs stay the same. So they're not changed. No change. Okay. This question, part C, I thought was a bit difficult because students may not have understood what a data latch was or how it's supposed to behave. So I think there needed to be some setup for that in order for students to be able to successfully answer it. But what a data latch does is you can store the value of signal lines when it's instructed to load it on. So you would have a loading signal, you would have an input data signals, and you would have your latch output data signals. So I'm going to call the inputs I1, I2 and I3, and they're going to connect to the D input of our flip-flop. And I'm going to call the outputs O1, O2 and O3, and they're going to be connected to the Q outputs of each flip-flop. And looking at the flip-flops truth table, you can see that if a 0 is on the D, then on the next clock pulse here, that'll get put onto the output. And so if we have a 0 on I1, then I give it a clocking edge on this clock here, that'll get put onto O1. And so that would be my loading signal. So I'm going to have my loading signal, and I want them to be all at the same time. Because that would make it a synchronous latch. So synchronous would mean all the outputs change at the same time. Now the only other thing we need to do here now is connect 0 volts onto all of these set and resets so that we don't have them floating. Okay, so you can see here we've got 3 data lines here, which I've labelled I1, I2 and I3, and those get loaded onto the 3 different flip-flops when a clock edge on this load signal is sent. Okay, so here's our D-type flip-flop set to toggle. So they kind of gave it away a bit there. And you'll notice that we've got an input frequency here, which is our square wave on it, and it's connected to our clock. Remembering that it toggles, and it's going to toggle on the positive going edge of my clock signal. So if we start at 0, then this clock edge here is going to make it change. It's going to make it change to a 1. And that's not going to change again until it sees another positive going edge. So it's going to stay all the way across to there, then it's going to toggle. Go all the way across to there, then it's going to toggle. Okay. So that's what the graph might look like. And you can see that this is going to change the frequency to be half. And I think that's it for part B.